Okay, now we're going to go ahead and do an example. So we're going to take all the stuff we learned in the reasoning video and then do an example with it, so figure out how to use it. Your homework will follow these examples pretty closely, at least in terms of the computational parts. It'll just be up to you to determine how to do the algebra to actually get to your results. So for our example, what we're going to consider is the function x squared times the natural log of x. Okay, and what we're going to do is use the properties of derivatives and the derivative tests we discussed before to find the following. So for part A, we'll find the intervals on which f is increasing or decreasing. In B, we're going to find a local maximum and minimum values of f. And in C, we're going to find intervals of concavity and inflection points. All right, so for parts A and B, we're going to use the first derivative and the first derivative test. So part A, if we want to find intervals where this increases or decreases, the first thing we need to do is find critical points, or I could say numbers, just like we did in section 4.1. So what I'm going to do is take my derivative. Okay, so f prime of x. Right here, since it's x squared times ln x, I have to use the product rule. So the derivative of the first function is 2x times the second function is ln x, plus the first function is x squared times the derivative of the second, which is 1 over x. Right? Now I want to set our derivative equal to 0, like we did in 4.1. This is equivalent to 2x ln x. And since I'm using this, I'm going to go ahead and simplify. So x squared over x is really just a plus x here. Right, so now I want to solve. I notice on the right I can factor out an x. So I have 0 equals x times 2 ln x plus 1, right? Since this is multiplication, I can set each part to 0. So I get x equals 0 and 2 ln x plus 1 equals 0. All right, so notice that in your original function, we have the natural log of x. Well, the natural log of 0 is never defined, so it doesn't even make sense to keep this first solution. So here, fx is not defined when x is 0, so we don't use that one. All right, let's go ahead and look at the second part of this. So coming over where the natural, this 2 ln x plus 1 is, if we solve this equation, we'd subtract the 1 and divide by 2 to get ln x is equal to negative 1/2. To isolate x, what we have to do is exponentiate each side by e. So if we do that on the left-hand side, the e will undo the natural log, leaving us with x. And if we do it on the right, we'd have e to the negative 1/2. So if you pop that in your calculator, you should get approximately 0.61, which will be useful for our next step. All right, so that part is exactly what we did in section 4.1. What we want to do now is go ahead and put this on a number line. So now I'm going to put this on a number line. Okay, I need to notice that since I have the natural log of x in my original function, this number line has to stop at 0, right? The domain of the natural log of x is all positive, so from 0 to infinity. So no matter what, my x values can't be lower than 0, and that's because of what the original function looks like. All right, I also need to put my critical value that I found in the first part of 0.61 on here. So I know I have e to the negative 1/2 is about 0.61. All right, so just to recap, okay, I know that the domain of my function is 0 or larger, so that's why I had to stop at 0. And then this right here was my critical value, so that's why I put that there.